This 9.2, sorry, 9.4 comparisons of series part 2. Now, in this part, we're going to introduce a different type of test called the limit comparison test. So here's a formula test. If A sub n is bigger than 0 and B sub n is bigger than 0, so that means all the term must be positive. For all n greater than or equal to absolute capital N is any positive integer. If the limit of the ratio A sub n over B sub n and approach infinity equals C, where C is any constant, positive, and it's not infinity, then both series converge or both diverge. Right, so think about it, what it means. When you have the series, okay, A sub n and B sub n, when the two of the two series, instead of comparing term by term, you forming the ratio, okay, we form the ratios. So it's like if we form the ratio here, A sub n over B sub n, of course the ratio of the terms are not the same, right? So if you have 2, 3, 4, 5, 6, so it's one series, right? And then you have 7, 8, 9, 10, etc., right? So if you have two series, if you form the ratio 2, 7, 3, 8, 4, 9, 5, 10, etc., the ratio would not be the same. But if I look at the ratio, take a limit n with infinity, so then you're looking at all of these ratio and see where it's approaching. If this ratio approach a constant C, any constant, it doesn't matter. Let's say if the approach, this one is smaller than 1, so let's say it's approach 1/2. Okay, so what does it mean? That means the series here has a term, has all the term, it's about half of these terms down here, right? So all the terms in one series A sub n, about half of each term in the B sub n series. Since the ratio is a half, the sum you expect to be about half. So that means the sum of the series A sub n is about half sum of B sub n. So that's why it says if A sub n converge, B sub n converge. If they converge, diverge. Because they get about some ratio, right? So they both converge and diverge at the same time. Okay, so a lot of time this comparison is more useful than direct comparison. Let's see. Now this test works well with series whose general term is rational functions. So you should expect to see a polynomial. This test works really well. Okay. Again, to find the comparison series, come up with the B sub n, we will keep the highest powers of numerator and denominator. We're going to keep the dominant terms as we did with the direct comparisons. Okay, let's look at this example here. 2n plus 1 over n plus 1 squared. Okay, so what we're going to do, you see this one is polynomial, that's really 2x plus 1 is a linear, and this is quadratic. So what we're going to do is going to compare this series with a equivalent and a known series, okay? And to come up with that series, I'm going to keep the dominant terms by dropping the insignificant terms. So when n is large, you see that these two, the one is nothing compared to 2n, right? And it's million and nothing. So I drop the ones, number 2n. And the denominators, again, the 1 compared to the n, it's nothing. Drop the 1, so you have an n, but don't forget the square. So it's a n squared. So it's going to behave like 2 over n, basically 2n over n squared or 2 over n, because when n is huge, then the 1 is really nothing. So that is a series or the term that we come up with. Now we will take the ratios of a sub n over b sub n, and the a sub n is that one here. B sub n is the one we just come up with, right? So you form the ratio, limit n approach infinity. Again, here's a sub n, it's b sub n. Okay, a sub n here, right here, and that's b sub n. Now, fraction divided by this fraction and multiplied by the reciprocal. So we time n over 2. So time n is 2 over here. Then from here you can take the limits and go to approach that n approach infinity. Notice that if you multiply it out, you can see it's 2n squared plus n here. This one you FOIL, it's n squared plus 2n plus 1. I think there is a typo here. That one you FOIL, we got that one, but we should have an extra 2 in front here. Okay, so that would make it 2n squared plus 4n plus 1. Now they have the same degree and the same degree in the top and bottom, so it's going to be leading coefficients over the leading coefficients. So the limits here will be just 1, right? So that limit is 1. What does it tell us? It tells us that the series here, we want to test, and the series that we come up with, 2 over n, what? Have about the same size. The ratio is 1, right? So ratio to consecutive, corresponding terms is 1. So in the term about the same. Hence, the sum is about the same. And hence, one term, one series converge, so does the other one. But I don't know about this, but I do know about the series that we come up with. Can you tell? This is really, if you take the 2 out, it can look something like 1 over n here. So you can see it in harmonic series, or the P series with P equal 1. So I know that this series diverges. Okay. Right, so that's harmonic series. And since harmonic series diverges, then the series we test also diverge. Okay. And that's by, I should say, this one diverges the series, okay. The series, I mean this one, the 2n plus 1 over the n plus 1 square. The series diverges by limit comparison test. Okay. Again, because the series diverge, that means this one is huge, go to infinity. And the term, the sum about the same, so that would be huge. It's approach infinity as well, and therefore diverges. Now let's look at another one. 1 over 2 to the n minus 1. Again, to come up with the series to compare with, we're going to drop the insignificant terms. In this case, well, nothing on the top, but the bottom, we can drop it minus 1. So when n is large, think about this. This term would behave like this. Again, what we do is we just want to compare the series with the series. Okay, that one and that one. This one we don't know, but we do know about this one. Okay, so now this is 1 over 2 plus 1 over 4 plus 1 over 8. You know, the one that we did earlier, I think in 9.2. See the time I have to get the next term. So that one is really geometric series. Now that is the known series. So we know it converges because of the R is 1/2. Okay, but before we get there, make sure you do a comparison first. So you can compare them to see if they are about the same size in the sum. Right, so take the limit, a sub n over b sub n. It's a sub n, that's b sub n, that one over that one. Multiply with reciprocal, take the limit, the top and bottom actually the same, so it's going to be 1 again. So because the limit is 1, and the both series converge, diverge at the same time, since the 1 over 2 to the n converges by geometric series, then the series we test also converges by limit comparison test. Okay. Now let's look at these examples here. We have 6 examples. Look at the first one. 1 over 4 to the n plus 5. Okay. Series right here. You see, that one is very similar to the one we did. Again, how do we come up with the series to test? The one that's the b sub n. Okay. Drop the 5. It's 1 over 4 to the n. That series, you do know this. What series is it? 1 over 4 to the n. That one is geometric series. Yeah, it's very similar, so I'm not gonna do it again. So that one is common ratio is 1/4, and so this series converges. Just give you the getting started here, getting started. But again, I'm not finished the problem, so you're gonna show more work when you do the test. Okay. If you look at number 2, n square, nq, see this polynomial, you're going to drop the -5n. That one is not very small compared to n squared. So again, by keeping the significant terms or dominant term, I have n squared dominant at the top, nq dominant at the bottom, right? And 1 is not much smaller than q. You simplify, that becomes 1 over n. And therefore, the series that you're going to compare with would be 1 over n. N from 1 to infinity. Again, this one we know diverges because it's harmonic series. Okay. Now from here, Again, you need to show the limit part. So that's the limit of the a sub n over b sub n, the n approach infinity. You need to show that. So this over this, but you should have the limit equal to 1. And since then, since this is 1, these two combine, you can conclude that the series we are testing diverges. Now keep in mind, we always have 2 steps. Checking the series, come up with a series and test that new series, then you do a comparison, and then you can conclude. Okay. The third series here, number 3, is the same. You see, you just follow the guidelines. That's a 3 in the top right. Just leave it there. Bottom, drop the thing. You're gonna find that is for n. So the b sub n series we have is 3 over square root of n or n to 1/2. So when you write the half, so you can recognize this series is a p series. With p series, p is 1/2 smaller than 1, so that series would diverge. Right, so the series we came up with would diverge. And then again, don't forget you have to do the limit of a sub n over b sub n and approach infinity. You got to do this. I believe it's got to 1 again. And then these two combine, conclude the series diverge. Okay. The first part, by the way, it's always the same. You have to come up with the right series to compare. Okay. Now let's 4, 5, 6 for you to do. But basically, for the 4, it's gonna be these 2, right? The 5, so that's 45. The 5 is a bit different. The 6 is this. Obviously over that. It's the n over n to the 7, 4. For number 5, it's different with the cosine. So that one gives you direct comparison, not limit comparisons. Remember the cosine of n with n, that's smaller than or equal to 1. So I'm going to use this compared to, you drop the 5, so it'll be 2n squared. And use direct comparison with number 5. Right? So that finishes the 9.4.